So welcome everybody to this QuSCo Nerd Talk today on December 7. I'm very happy to introduce this talk because it's going to be given by one of my colleagues since I started this PhD, who has done an incredible job and trying to understand some of the more theoretical details on Qubit and on more analytical studies of systems. And in particular, today I'm very happy to introduce Daniel Basilewicz, who is going to talk to us about these fundamental bounds on qubit research. So whenever you want, Daniel, stage is yours.
Okay. Thanks, Fernando. And as Fernando introduced, I'm going to talk about, can you see my pointer, mouse pointer?
Yes.
Okay, perfect. So as Fernando mentioned, I'm going to talk about qubit reset. So let me briefly phrase what the problem in qubit reset is. So let's assume we have a qubit, which is initially in the ground state, but we are using it in some kind of computation. It's coupling to its environment, so over time it will become mixed. And it becoming mixed means physically that the entropy within captured in the qubit is increasing over time. So what we need to do is we want to get rid of this entropy, and we have to do this in some kind of controlled way. So for example, using some kind of control field, and we have to export the entropy, well, outside of the qubit and also not into another qubit. So we need to export the entropy into the environment. And ideally, such a reset process, if we switch off, for example, the control field, we would want the qubit to be again in the ground state. And of course, as long as the control field stays off, also the entropy is not flowing back from the environment into the qubit. So why is qubit reset interesting and what are the challenging? So typically the state before the reset, so which can be any mixed state, is usually not known. So what we need to find is a reset process that works for all initial states. Then reset is also typically really slow compared to other operations that you can run on your qubit. And also your qubit needs to reset. Your reset needs to this external system, the environment, as an entropy dump, and that's also the reason why it's slow, because typically you want your qubit to couple as less as possible to the environment, and this of course also means that if you need the coupling to an environment for the dumping of the entropy, then it takes a long time. So that's kind of the crux here. So you really want to be fast, but you don't want to have a large coupling to environment. So to somehow resolve this problem, we considered a particular model, namely we assumed that we have a structured environment. Namely, we assumed that our environment is given by a strongly coupling ancilla. So we assume that the qubit coupled strongly to some kind of ancilla system in the environment. And then there's the reigning environment, which could be, for example, some thermal reservoir, but its dynamics is completely given by Markovian dynamics. And now the question is, how do we have to choose the control field such as to initiate the export of the entropy, which means to initiate the qubit reset? And what we asked ourselves is, qubit reset in for such a model possible? And also another important question, since I mentioned that the qubit will be strongly coupled to the ancilla, we might have some initial correlation between the qubit and the environment, namely between qubit and ancilla. And is it possible to erase those kind of correlations, and what does it do to the reset process? So how does it affect it? And we started with a really simple model. So we assumed that the qubit and the ancilla are really two-level systems with a fixed energy levels between omega q and omega a. And we assumed that our control field couples via sigma z. So which means it's a frequency tunable qubit, more or less. So with a control field we can change omega q, or the energy level splitting of your two states effectively. So since we have the strong coupling and we are only interested in the dynamics of the qubit, that would require us to model the dynamics of the qubit as a non-Markovian dynamics, which is of course difficult numerically. So what we did here is that we assumed, we considered numerically the system of qubit and ancilla, and we picked the Hamiltonian of this system to be omega q tensor 1, 1 tensor omega HA, and then we assumed a coupling between qubit and ancilla by a coupling constant J and a coupling of sigma x times sigma x. And then we modeled the influence of the remaining environment, so as a Markovian evolution, so we assumed the environment to be at some finite temperature, so it gives rise to a cooling and a heating term. And we modeled the dynamics of the bipartite system of qubit and ancilla with the Lindblad master equation. And now to check whether we can reset the qubit with, in such a system, we've first started to assume factorizing initial conditions. So we assumed the initial state of the bipartite system to be a factorized state of a thermal equilibrium state of the qubit times the thermal equilibrium state of the ancilla. And for both, the equation for a thermal equilibrium state reads like this. So the important point to notice here that there are two quantities that affect your thermal equilibrium state. On the one hand, it's the energy level splitting of either qubit or ancilla, and on the other hand, it's the temperature of this system, particular system. And as I mentioned initially, what we need is to export entropy. So we need to dump the entropy somewhere, and as you might have guessed, we need to dump it in the environment, and here we want to use the ancilla, explicitly the ancilla, because we have a strong coupling between qubit and ancilla, so we can expect this dumping process to happen much faster than with a slow coupling to the environment. However, in order to be able to dump entropy from the qubit to the ancilla, we need this quantity to hold, which is that the purity of the qubit is initially smaller, or basically other way around, that the purity of the ancilla is initially larger than the purity of the qubit. This means that the ancilla has initially less entropy, so it can basically take entropy from the qubit. So the question is, how can we ensure this? And there are, just looking at this equation, only two possibilities. One would be to assume different temperatures of qubit and ancilla, but that's of course unphysical. So the other obvious choice is that we just assume that the ancilla has just a larger energy level splitting than the qubit. So this is also easy to realize in an experiment. And just due to that, we can already ensure that the qubit is that the ancilla is initially more pure than the qubit. And then our optimization task, we want to reset the qubit, which means we want to maximize its ground state population, and as an optimization functional, then I picked this 1 minus the final state of the qubit and its overlap with our target state in the qubit, and the target state will be just the ground state. So this is equivalent to 1 minus the ground state population. So it's 0 if 100% population is the ground state and strictly larger otherwise. And then I checked some numerical results first. So what you can see here in the upper plot is the ground state population of the qubit and the ancilla under those parameters. And as you can see, as long as the control field is switched off, so no control field, the ground state population more or less stay on their initial levels. This is also what you can expect, because the qubit and the ancilla are far detuned from each other, so effectively they are not really talking to each other, despite the rather large coupling between them. So
Daniel,
if you know...
Would I ask a quick question?
Sure.
So actually I was wondering about the initial thermal state.
Sure.
So do you think this is the same as, so as model here is the same as you would get by doing a thermal state of the dressed system?
Yes, I will come to that in a minute.
Okay, thanks.
It's not the same, but I will come to that.
Okay, that's great because I actually do the other way.
No.
And I want to know which one's the right one.
It will just check what happens for factorizing initial states.
Okay, thanks.
So if we assume both systems to be factorized initially, then okay. So if you see this dotted dynamics, and now if you switch on a control field, and we assumed, okay, probably putting both systems into resonance is a good choice. Then you can see that the qubit ground state population smoothly increases to some kind of maximum and then decreases again, and we have also kind of same oscillations in the ancilla ground state population. And now if we ask about, okay, let's maximize the qubit ground state population, we can do this with optimal control. And then what you can see, yes, we are able to maximize the qubit ground state population at final time, but we are not able to overcome the ground state, so to reach more ground state population than what we had initially in the ancilla. And we also tried with a lot of different gas fields and different control schemes. And what I can show you later, yes, that's the time optimal solution to put both systems into resonance. You're not able to reach more ground state population than what you have in the ancilla initially, and you can also not do it faster than in pi over 2j for the given parameters here amounts to 15.7 time units. But of course we were interested in correlated initial states, and a natural correlated initial state is of course the steady state of the coupled system of qubit and ancilla, and this has this structure. I'm not going to show you the details of these factors because they are rather long expressions, but the important thing is this is while the factorized initial state that I showed you before is a purely diagonal state, so it has no off-diagonal elements here. The correlations are created by these off-diagonal elements here. If you want to quantify the correlation strength, you can do this using the mutual information, and it's a rather weakly correlated initial state, so the correlations is on the order of 10 to the minus 3, so that's not a lot. But if you try to do the same strategy as before, you're able to reset the qubit as well, and you're actually able to reach exactly the limit that you were able we were able to identify for a factorizing initial. So it doesn't seem that the initial correlations are bad here. However, they are small. So what we were really asking, what happens if the systems are strongly correlated? So we were looking for initial state that allows for varying the correlation strength and also to increase it. And to this end, we consider this state, which is the factorizing state with both systems in a thermal equilibrium plus this additional term here, with gamma being a real and negative parameter, and this is motivated by this natural choice of the because from the off-diagonal elements, those two, so the theta minus were the larger ones, they were real and they were negative. So we were motivated, okay, so let's take this state as a good way to increase the correlation strength smoothly. So this is nice, and it has also the advantage, so if you take the reduced states of qubit and ancilla from this initial state, the reduced states are unaffected by the choice of gamma here. So it's not that you're increasing simply the purity of the qubit and ancilla initially. So it's really only adding correlations between both systems. And what I show you now in this plot are optimization results for two different kind of questions that we asked. So in the upper plot, we asked, please, or basically it's an observation that we made. So we observed that we can reach errors that are below what we were able with factorizing initial conditions. So on the x-axis you see here the increase of the mutual information. So it's an increase of the initial correlation strength. And here in the top plot we asked how fast can we actually reach a reset error below the reset error that was given by the factorizing initial state. And you can see the more initial correlations you have, the faster you can actually reach that. And in the lower plot, we were asking the question, okay, we don't care about the time it takes, what is simply the lowest reset error that we can achieve? And here you can see the more initial correlations you have between qubit and ancilla, the better you can reset the qubit in terms of error. So the important thing that we got from this here is that initial correlations actually allow you for better and faster qubit reset. And so they are not a nuisance, they are really an asset here for the reset process. And then we ask ourselves, so can we understand this also roughly analytically, what's going on? And to this end, this was the Lindblad master equation of the qubit ancilla system that we use to model our dynamics. And yes, you can understand what's going on analytically, but you have to do some approximation. Namely, you have to neglect the thermal reservoir, and you have to apply a rotating wave approximation. It's okay to neglect the thermal reservoir because, yes, it's important for the entire process to work, because the thermal reservoir makes sure that the ancilla thermalizes over time, and you have actually this initial ancilla state with a high purity. However, for the fast reset process between qubit and ancilla, the reservoir is not important. So it's a fine approximation here. So we will only consider such an equation, and I'm not going to go into the details, but I just want to briefly motivate what the key ideas are. So you can assume your qubit ancilla state to be a 4 times 4 density matrix, so it has 16 elements, and by choosing, so you can assume or write this entire differential equation as a vector form, and by picking like the right transformation, you can transform the entire equation of motion such that it becomes a 3-dimensional problem, with only Z1, Z2, and Z3 being relevant. And why this is interesting, I will show you right now, because this equation of motion describes the motion on the surface of a sphere. So what you are able to do is you are able to define some radius r, defined by the initial values of Z1, Z2, and Z3, and C. And this radius is a conserved quantity. And you can assume that you have a sphere located at this, with its center being at C, 0, 0, and the coordinates being Z1, Z2, and Z3. And now the important thing why this is an interesting equation of motion is that Z1 is more or less equivalent to the qubit ground state population, and Z2 and Z3 reflect the imaginary and real part of the correlation strength. So it describes the entire dynamics for this kind of initial state. And previously we were interested in minimizing the qubit ground, or maximizing the qubit ground state population, and here it really becomes just maximize Z1. So your function that you want to minimize is 1 minus Z1, and you simply have a 3-dimensional system. And for the case that you say both systems are in resonance, qubit and ancilla, you actually even become a 2-dimensional problem. So you only need Z1 and Z2. And already in this equation of motion, you don't even have to look at the dynamics. You already understand why you are able to reach, with initial correlations, larger Z1 values than you would be able without initial correlations. And the reason for that is simply the radius r. So if you assume you have no initial correlations, we know that Z2 and Z3 are initially 0. So our radius is entirely given by Z1 and C, and Z1 and C is given by the thermal equilibrium states of qubit and ancilla. However, if you have initial correlations, those two states remain unchanged. Z1 and Z2 remain unchanged, but Z2 and Z3 might become non-zero, so your radius increases, while your center of your sphere remains identical. So that already tells you, yes, if your motion is restricted to the surface, then you are able to reach Z1 values that are much larger than before. So what I want to show you just quickly here, if you have factorizing initial states, you can also understand the reset protocol simply in this with a resonant driving field. So your initial state is something like this. So in this blue bars, you see the vector field given by this, and what you're performing is just a half circle. So your state will move along this green light until it reaches this point, which is the point of largest Z1 value. Then you should go out of resonance, because otherwise you would go back and lose purity again. And so this is for a simple resonant case and for factorizing initial state, but for correlated initial states, it's not able to solve this equation of motion analytically. But what you can do, you can solve it numerically and then try to understand what happens here, what the reset protocol is doing. And that's actually really simple to understand, and also gives you an explanation why it's faster. So with initial correlations, we have in this case Z3 being initially non-zero, so we start at this point on the sphere. And then what the optimized field that you can see here does, it performs a fast kick from here, more or less to the plane being equivalent to Z3 equal to 0, then going into resonance and performing a slow motion here to the state with the largest Z1 value. And since this initial kick is really fast, and this we have to overcome a distance which is less than half the circle that we have to do here. And therefore you can also see geometrically why it's faster, the reset with these kind of initial correlations. And with this I would like to add an intermediate summary of what I have showed you so far. So what I showed you is that Qubit reset is feasible for factorized and correlated initial state, and we can, with simple experimental feasible drives, that we can actually understand how they work. So for factorized initial state, the purity swap with the ancilla is the optimal solution, and the minimal time is determined by the coupling strength, so pi over 2j. And what I also showed you, that if you have correlated initial state, then you are able to reach purities or ground state populations that are beyond the initial purity or ground state population of the ancilla, and that also in time faster than what you have for factorizing initial state. So correlations are really a resource here for the reset protocol. Are there any questions so far?
Maybe a quick question.
Sure.
So how would one realize these correlations in practice?
That depends, I mean, what we checked is if you would increase, so I mean, we modeled this, and we also modeled this with different coupling strengths. So yes, this is a weakly correlated state, but if you would assume larger coupling values between qubit and ancilla, you would also probably get more mutual information and more correlations initially. However, that was then another idea that we had, which is not part of the project so far, that we were thinking about if correlations are initially a resource, maybe it's also able to explicitly create them for the reset purpose and check whether this gives you some benefit. But right now, the only answer that I can give you is if you have larger coupling between both systems, you will naturally get more correlations.
But then if you have larger coupling, you would have either that the frequencies are closer, in which case your reservoir has less space to collect entropy, let's say, right? Or that the coupling is much stronger, and I'm not sure how then the result extends. I can't see it, but it's not clear if for the, so say if one tried to remake the same results, but where the correlation is now physically derived, then if one can obtain the same improvement.
Yeah, it's a question that needs to be answered that I cannot answer on the spot, I have to admit.
Okay, no, but it's
interesting question. But here it was rather an observation, so what happens with initial correlations, and sure, there are other questions that arise from that, of course.
Yeah. Okay, thanks.
No problem.
Thank you.
So if there are no other question, I would then come to the next part, namely, so what have we considered so far? So we assumed Qubit, the qubit to couple to a structured environment with a large coupling to the ancilla and the reservoir, and we assumed the qubit to be a frequently tunable qubit, so we have some kind of control field that allows you to basically change energy level with splitting, and we assumed a sigma x times sigma x type of interaction between qubit and ancilla. However, now we are generalizing the model slightly. Also, we neglect the reservoir in the following, which I already told you before, why this is an okay approximation for if you're only interested in the dynamic between qubit and ancilla. Next, we assume a general type of control, so we exchange the sigma z type of control with some O control, so some unspecified operator O control, and we also exchange interaction with some general operators OQ times OA. And ask the question, so is a reset possible for all combinations of those three operators? And also, is a reset strategy if yes? How does the strategy, the fidelity, or the time depend on those three parameters? And what we were interested in, I will show you in this kind of overview picture. So we considered 9 different interactions. So sigma x, sigma x, sigma x, sigma y, and so on and so forth. And for each of these interactions, we considered 3 different coupling mechanisms of the field to our qubit. Again, sigma x, sigma y, sigma z. So we have 27 combinations, and we were asking ourselves for which of those combinations can we reset the qubit. And one answer I can already give you. So the sigma x interaction with the sigma z control, I have shown you before. Yes, in this case we can reset. So the question is basically for which 26 combinations we can reset the qubit. And to answer this question, it's already able to, you can answer this question already on the level of the Hamiltonian without having a look at the dynamics, and I can show you in the following how you can do this. It uses the Cartan decomposition and the Weyl chamber as analytical or mathematical tools. So in this part, we also assume qubit and ancilla to be initially factorized. So we assume we have some general time evolution operator U. So the dynamics of the qubit can be written in form of this dynamical map that depends on time, and it depends parametrically also on the initial state of the ancilla. And we are asking ourselves, in which case is this dynamical map able to purify the qubit, so reach purities beyond the initial purity of the qubit. And there's a simple quantity that you can check, namely non-unitality. So you can show that you can perform a qubit reset exactly when the dynamical map is non-unital, and non-unitality means it's not mapping the identity operation to itself. So we simply have to check this quantity. However, we want to ask a really simple, so the question for which kind of operators does this does the dynamical map here be non-unitary, because it somehow enters via this equation here. And just in brevity, so we're using the Cartan decomposition of SU4 to this end, which means you can write every element U of SU4 as K times A times K prime, and K prime being entirely local operations that are not changing the interaction between, the entanglement between the two systems, and also not the purity of the two systems. So you can basically forget about this. And A is the non-local part of the operations, and we know we want to exchange purity, so the purity exchange has to be given by the non-local part A here. So how can we check non-unitality? So we plug this Cartan decomposition into this quantity above, do some math, and then we see, okay, non-unitality is given by this with this. Oh, I forgot one step. So we start with initial step of the qubit being the identity matrix and the ancilla being like a general state. So we're not specifying the ancilla state. Then plugging in the Cartan decomposition, we see, okay, we get a locally transformed ancilla state, which is not changing its purity, but it's somehow rotated in space. And then we only have the non-local part A here left. And then we have to check in which case does this give an identity matrix. And then you will find it gives you an identity matrix plus those three terms. So the question is, when do those three terms vanish or not vanish? And here you can find they vanish exactly if at least, they vanish if only one of those coefficients is zero, is non-zero, so two of them are zero, then those three terms are vanishing. So let's assume C1 is non-zero, but C2 and C3 are zero. Then you can see that in each of those three terms you have at least one sign term which becomes zero, so all three terms vanish. If you have at least two non-zero coordinates here, then at least one of those terms does not vanish. So this is an easy property, and this kind of how many of these non-local coordinates C1, C2 or C3 vanishes, you can already see from the Hamiltonian with this kind of analysis tools, which I'm not going to go into much more detail. So what we can find is, answer the question is for a lot of those combinations of interaction and local control, you can at least have two non-local, two non-vanishing non-local coefficients, but for some of them you can only have one. And we know that with only one of those coefficients being non-zero, we are not able to reset the qubit because it gives you us a purely unital dynamics. And with unital dynamics, we cannot reset the qubit. So the interesting result is here only 16 of the 27 combinations allow you to reset the qubit, despite the fact that you can build entanglement between both systems in all cases. So that's an interesting observation here. So the obvious next question was, how does a qubit reset look in each of these 16 combinations? And the answer to this, we again try to tackle it numerically. And what I can show you here, is the evolution of the purity for a thermal equilibrium state of the ancilla and 100 randomly chosen initial qubit states, despite the under the fact that they're all identical in purity initially. And then putting them into resonance, you see that you reach some kind of maximum in the qubit purity at some time, then it's going back, down, and up again. So this is for sigma x coupling and a sigma z control. What you can find out is that there is in fact an upper and a lower shape, which you can determine analytically, and I will do that on the next slide, and that there is also minimal time. However, what we were asking ourselves here is, can you actually speed up qubit purification by means of using a non-resonant protocol, so some kind of time-dependent protocol? And what you see here is an optimization result for every time choosing a random initial state and trying to maximize the qubit purity at the final times here given. And as you can see, with the final results given as red dots, it's not possible to reach a higher purity than what's given by this upper shape here, and it's also not possible to reach the maximum qubit purity in less time than t-min. Also, after that, you're of course able to always reach the upper limit here. We can check that also for different combination here. Again, sigma x coupling, but now with the sigma x control instead of the sigma z control. And you can see we see a similar behavior, but the qubit reset takes more time. And again, we can do the numerical check, And yes, we are also not able to be faster than this T-min here. We can, for example, change the interaction here. Now we have a sigma x, sigma y interaction, and we will see the same behavior. And I also checked other combinations that I'm not showing you here, but you will see the same behavior. So what you can observe from this numerical results is that a purity swap under a constant resonant field remains the time optimal solution, or at least it appears to be the time optimal solution. However, the minimum reset time seems to depend on the choice of local control and your interaction between qubit and ancilla. So as I promised, I have also an analytical formula for the purity and also the shapes here shown in blue, and the approximation. Not sure whether you can see it. So this is a numerical simulation without an approximation, and this is an analytical approximation that we came up with. Same here, so we kind of get the same evolution despite that we are losing these wiggles here, but they are not relevant for the reset time. And so this formula that we are able to derive uses an arbitrary initial state of the qubit and a thermal equilibrium state of the ancilla, so we don't have any ancilla coherences initially. And for such a general initial state of the bipartite system, the evolution of the qubit purity under a constant resonant field is given by this equation, from which we can also find an analytical equation for the reset time, which is pi over 2 eta, and eta depends on the actual choice of the coupling mechanisms here, type of interaction and qubit control. So it's different for all of these cases. And we are identifying indeed the 3 different reset times, which are roughly T1, so given by this, where T1 min is really the fastest one with pi over 2j, and the other 2 are slightly larger. So out of these 16 combinations that allow for qubit reset, only 8 of those 16 combinations are really the fast ones, if you want to perform it as fast as possible, despite the fact that the remaining combinations are of course time optimal. So there's just no way to perform it faster than that. And now the last point that I want to talk about is what now happens if we consider higher dimensional systems or ancilla. And again, that's a purely mathematical argument here. So let's again consider the equation of motion for the qubit and say, let's assume that we have a qdit and an ancilla with dimension dq and dA. So our time evolution operator will be an element of SU dq times dA. To answer the question what then happens to the reset time, that's not possible to answer analytically. However, we did some numerical studies, and at least we didn't find a strategy that's able to reset the system faster than pi over 2j. So it appears that this remains the time optimal solution. The fastest time at least. However, for the reset fidelity, things change here. So, and to make this clear, let us assume that the initial states of our qubit and our ancilla are given in their eigenbasis. So we have some kind of spectrum Qi and a spectrum Aj, which describes the initial state of the qubit and the initial state of the ancilla. The bipartite system then has some kind of spectrum given by lambda ij, with lambda ij being Qi times Aj. So we can write it like this. Then we assume that our time evolution also yields a factorized state, which is a good assumption because, of course, you don't want your reset to correlate your qubit with an ancilla. So you want your U to also give you a factorizing state on output. And therefore, we can also write the final qubit state here indicated with a prime in their eigenbases and also the joint state of that, and we are having the spectrum lambda ij prime, which is qi prime aj prime, so basically identical to the initial state. And having this final state, the qubit purity then reads like this, so it's the sum of all qi prime squared, with qi prime being the sum of all lambda aj sums over all j's. And now one important thing needs to be noticed. So we know that this is a unitary operation. So, and a unitary operation leaves the spectrum of your the spectrum invariant. So the spectrum of rho and rho prime will be identical. However, identical doesn't mean that you cannot reshuffle it, and U is indeed capable of reshuffling the spectrum. And maximizing the qubit purity therefore means maximizing, reshuffling the spectrum appropriately. And what appropriately means, I will tell you right now. So in the first step, what U needs to do, it has to reshuffle the dA largest value of the initial spectrum such that it maximizes the values lambda 1 j prime. And by doing this, this will maximize Q1 prime to the maximum, which is actually possible. Then, next step, we need to it has to reshuffle the dA largest remaining values, so subtracted with the dA previous one, such that it maximizes lambda 2 j prime. So this will maximize Q2 prime, and so on and so forth. And I will also give you like a graphical idea what's happening. So let's assume we have a qubit again, and the qubit state is given by the by the spectrum Q1, Q2. We assume a dA dimensional ancilla with its spectrum being A1, A2 until ADA. So the spectrum for the joint state of qubit and ancilla looks like this. Lambda 1, 1 is given by the product of Q1, A1, and so on and so forth. And now what we know, what our unitary operation is capable of, it can reshuffle this spectrum in a new way. And if we choose this U such that it ensures that the dA first eigenvalues are larger than all the dA, well, the other ones, then this will maximize Q1 prime, and this will, without restriction of generality, maximize the qubit purity, and it's the maximum that you can reach. So why is this interesting? This I will show you now in the final example. So let's assume our qubit is in a completely mixed state. So its spectrum is 0.5, 0.5. And we have a 4-dimensional ancilla with a spectrum 05, 05, 0, and 0. So both of these states are mixed states. So the spectrum of the joint state reads like this, and we know a U exists that is able to reshuffle all the 0.25 values into the first part and the zeros into the second part. And since the Q1 prime is the sum of those four values, we obtain that Q1 prime is 1 and Q2 prime is 0. So we have a perfectly pure state generated from two mixed states and uncorrelated state initially. So higher dimensional ancilla allow you to reset your qubit beyond a simple swap of purities. So this is a really nice result, and with this I would like to come to the summary. So what I showed you in the second part is that the feasibility and performance of qubit reset really depend on the type of the interaction between qubit and ancilla, and also the controls, type of control with which the control field interacts with your qubit. Whether qubit reset is feasible, you can determine already on the level of the Hamiltonian. The fidelity of the reset, if you have an uncorrelated initial state, is basically given by the maximal, by a perfect swap of purity, at least if you have a two-level ancilla and a perfect qubit. The reset time, despite the fact that a resonant drive is always a time to optimal solution, gives rise to 3 different timescales for the qubit reset. And finally, if you have higher dimensional ancilla, this actually allows you to reset your qubit beyond a simple swap of purity if you can at least engineer those kind of unitary operations, because we didn't make any claim on how to generate them. We just know that they exist. So the take-home message is that if you are able to engineer your architecture for your qubits and for your reset in some way, you probably should take some care, because not all of these architectures are equivalently well suited for qubit reset. And with this, I would want to like to thank all my collaborators and, of course, for your attention.
Thank you very much, Daniel, for your great talk. I would kindly ask the audience, if possible, to unmute yourself and give a big clap of hands for to Daniel. And if there are any questions in the audience, please, now is the right time to ask. Okay, then I will start with a very simple question. You say that higher dimensional ancilla already allows for a better performance rather than just swapping the purities. Does it increase are the results better the higher the dimension, or does it cap at some point, or is it just a quality factor that just applies in a 3-level system for the ancilla?
No, there are 2 things that actually enter in how large the purity can become. So the dimension is in fact one part of that, but also, of course, just the initial spectrum of your ancilla. So because here I was making up this example here with 0.5, 0.500, and if you have here, for example, also a completely mixed state, then of course you also can't do anything. So it's not simply an argument of the dimension, but it's also an argument of the dimension. So for example, if you here assume that we have simply a 3-dimensional ancilla, so 0.5, 0.50, then you could never reach, I think, a pure state. If I'm not doing the math wrong right now. Okay, and I mean, in the reference that I don't want to give a wrong answer right now. So in the reference here, that we actually found a formula that tells you how pure or how close you can get to a pure state, if depending on the initial spectrum of your ancilla and also depending on the dimension of the ancilla.
Okay, thank you very much.
I have a quick question. So does the system of the ancilla connected to the qubit that you considered also account for the possibility, or does it, let's say, does it include within its realm the possibility of doing like measurement reset, where you actually measure the state and then depending on this?
We did not account for that, but as far as I know, measurement reset is also rather slow.
I think this is true because the coupling is not strong between.
And I mean, it's only one possibility to do a qubit reset. This kind of model that we used, exactly, and we really wanted to do a fast qubit reset and a fast reset. I mean, since you need to export entropy, the entropy export has to be go over some channel that allows for fast coupling, so or strong coupling, and therefore we assumed a strong coupling to the ancilla. But yes, we didn't account for measurements.
Okay, thank you.
Okay, Daniel, thank you very much for your talk.
Thanks for giving me the opportunity.
And of course, good luck for next week again.
Thanks.
To everyone, thank you, and we will see each other for the next appointment in January or February. Thank you very much.
Thanks again for the talk. Bye.
Thank you.
Thank you.